Yeah, thanks everyone for attending, and thank you Nikolai and his lab members, Mike, in particular, for organizing this. I believe this is a truly helpful thing for the community. Given all the hot things that are happening for AI, I think it's important for the College of Medicine colleagues, or Penn State in general, to be aware of this and to actually incorporate AI into your research, no matter whether it's basic science or clinical research, and also in clinical translations. And I'm more than happy to share a little bit about the one of the topics related to bias-variance trade-off and overfitting in machine learning. As Mike mentioned, I am a professor, and I'm also the interim lead for the bioinformatics and artificial intelligence goal for the strategic plan. So I'm really excited about the workshop and very grateful that Nikolai involved me in this efforts. So I'm going to talk about some overview of machine learning, which I believe you have heard at least some in this morning's session. And then I will talk about some comparisons between classical machine learning and deep learning models. And one particular thing that distinguish deep learning models is its complexity, right? So it can be used to solve very complex problems in real applications, no matter whether it's in medicine or in your daily life. So why does it work so well? I mean, what is superior for the deep learning models compared to classical machine learning models? And why the deep learning models doesn't have some of the concerns the classical machine learning methods have, like, for example, overly complex models tend to overfit the data. Why deep learning models seem to be immune from that, at least in some applications. And I'm going to talk about, wrap up by talking about double descent, which is more of an empirical observation. The theory behind that is not completely known, but it's indeed helped clarify some of the remarkable performance that you see in deep learning models. So machine learning, I think, differs from traditional programming, which is sort of deterministic, in the sense that they take input and they combine with some programs, and then they produce output. And machine learning basically is a more flexible thing. You can give them data, and together with some output, it can provide something that is more dynamic and can take further input from users, just like, I don't know how many of you know ChatGPT, and also the GitHub Copilot. You can basically tell them what you want to do, and it's going to give you a sample code. Sometimes it works, sometimes it not, but at least it gives you a program that allows you to further refine and actually take additional input. So that's kind of a remarkable thing that is enabled by modern machine learning that's distinguished from traditional programming and statistics. In machine learning, there are two major types of machine learning. One is supervised learning. So basically, you have labeled data, right? So you have a set of pictures, and you have labels on the pictures saying whether it's a human, it's a dog, or it's a cat. And then your machine learning algorithms could learn from the connections between the images and the labels. And then later on, when you only have the images, it can tell you which is contained in the image by the model that you train. So that is something that you would know the truth. At least somebody would know the truth. And then you can use machine learning to mimic the human cognitive behavior and to learn to automatically label the data later on. And another type of machine learning is the unsupervised learning, which you do not have the label. So basically, you try to learn the distribution of the data and see how many components are there in the data, right? So a lot of the unsupervised learning algorithms could be perceived as some kind of clustering. You can see people who are working on biology, if you work on microbiome, you see the tree of life is basically organized by different hierarchy, and you can cluster the bacteria into different genus or different species, and then, of course, those clustering could later be refined. You can either merge the cluster or you can further split the cluster. So those are things that you do not necessarily have a ground truth, but instead you try to learn the structures of the data from machine learning algorithms. So for this lecture, I will primarily focus on supervised learning. So one of the classical examples of supervised learning is how can you tell the digits from the handwritten digits. So a lot of the previously, if you mail a letter, I think the post office will have to manually sort those, which I think given the amount of mails that are received each day, I think it's going to be a very laborious task. But so people are trying to figure out whether they can train a computer to do that. And that's actually one of the very classical machine learning examples that are seen in almost all the introductory textbooks. This is largely considered a solved problem, which many machine learning algorithms could do reasonably well, even for the simple methods like regression, or even tree-based method like random forest could do reasonably well and could more or less attain human-level accuracy. And if you look at the actual digits, it's not as not entirely trivial. I mean, people write 5, people write 4 very differently. Like, I came from China, the way I write 4 is different from a lot of people write here in the States. And also a lot of the digits, like people write 8, sometimes, one of the circles is too small. I mean, it's not entirely a trivial task, but, the classical machine learning algorithms could do reasonably well there already. And in regard to the type of classical machine learning models, linear regression is, if you label that as a machine learning algorithm, it is the most basic one. So basically, you can consider a simple problem with 2 sets of dots, orange and blue. And then you have a set of features that are measured in x, which you can essentially regress the label over x. And then later on, you can use your regression model to make classifications of the dots having the orange color and the blue color. And tree-based method is another very useful approach. I think it's no stranger to people in biology and medicine, in that there's a lot of decision-making process that is essentially following a tree. And also people work on biology or work on electronic health record. You would see that there are different subtypes of disease. There are different species of bacteria that are naturally organized as a tree. And then you can, by asking a set of simple yes or no questions, and you can basically split the data into different clusters. And then each one of them will have a label. And you can split the different data points until each one of the terminal node contains only one entry. That's not necessarily the best way of running the tree model. On the other hand, you may actually prefer to collapse some nodes so that you're not over classifying the data, making sure that it can extrapolate well. And most of the AI deep learning stuff that is in the news these days are based upon neural networks. Neural network is a type of model that is organized as a network, and you have different nodes and you have different branches, edges that connecting different nodes. And the remarkable thing is each of the edge represents a very simplistic transformation of the data. But since the model can go very deep and you can have many parameters, the model can get infinitely complex and actually is working remarkably well in a lot of the applications, one of which is the image classification problem. The example that I mentioned, cat versus dog versus human, is the very simple simplification for that. In reality, you may have numerous categories, and actually one of the remarkable feat in machine learning is that people created a ImageNet challenge where they essentially crowdsource the labeling task across the community and asking people across the internet to label, what are in the image, and those provided some very useful training data for people to train their machine learning algorithms. And indeed, you can see those algorithms are starting to play a lot of useful tasks in our daily life. One of the simple example is the cat versus dog classification. And obviously, the cat has ticked ears, and the face is more round, and those features could potentially enable the classification. And cat likes to hide, so it's not often as simple as looking at the shape of the face or the ear, because they can actually hide within a bag or only show half of their face. So the machine learning algorithms can actually extract more subtle features in the image that can allow the classification. And the remarkable thing is that these subtle features are extracted automatically. So you don't really have to manually curate this. That's another reason why the deep learning methods is becoming popular. And in addition to classification, there are a lot of other complex tasks, including object localization, object detection, and segmentation. Basically, you can get the contours of the images, and also video processing. Not only something static, but also something that is moving. You can actually capture that really nicely. And one thing that I have to warn everyone here is that Pennsylvania police already implemented AI algorithms to look at your license plate, and they will very quickly know whether your registration expired or not. I actually had my first-hand experience last week. But those algorithms are highly accurate, and it's actually not that complex. For people in my deep learning class, I think they can actually write a functional program identifying license plate relatively straightforwardly after a semester, of course. So I think a lot of these applications really matters a lot in our daily life. And also there are medical applications, measuring the potassium levels through these wearable bands. So potassium levels is naturally measured in the blood, but you don't want to puncture your finger all the time. I think instead they can measure that from EKG. And also, the dermatologist can actually use machine learning algorithms to identify skin cancers based upon the neural networks. The reason that, and also more recent progress like ChatGPT and the protein structure prediction are something that is really impacting every aspects of our research and education mission. And of course, in our College of Medicine, we make artificial intelligence part of the strategic plan, emphasizing the importance of that in the next few years, which I think is highly timely and visionary, which I think part of this workshop is playing a very positive role in terms of the strategic plan. So you can actually see these algorithms are really performing very nicely. For going back to the image classification problem, you can see how these algorithms evolve over the years. And everything is representing, every bar represents an algorithm except for the red one, which is actually us, humans. And you can see actually since, I think, 2015, the algorithms can already surpass human in terms of classifying the images. And the reason that they can do so nicely is because they can fit very complex models. And for people who have experiences with statistical learning, you may wonder how come such a complex model play works so nicely. So I think that's going to be something that we will cover. And so one of the latest, relatively recent development, the Google Knight, contains millions of parameters. So so those are something that that is highly complex. That is not commonly seen in classical machine learning, but it ended up working so nicely. So so I want to go back to the basics and talk about the bias-variance trade-off and overfitting, which is something that relates the complexity of the model with its performance. So we have, we don't go with very complex model. We just start with a toy example, which you have a truth, which is kind of a parabola type of shape, and then you have some random noise in your data, and you observe something like this, right? So a lot of the machine learning algorithms try to essentially identify relationships between variables, and you have something observed, you try to identify the underlying model for this, right? So so you have the training data that you use to train the model, and then you have test data to evaluate the actual performance. And you can do this by a linear model, which has only one parameter, and so you fit and you get a straight line. And you can have a connect dot model, which actually fit the data perfectly, basically just connecting the dots as x involved. And that's actually going to fit the data perfectly accurately in the training data. So for the two model, I think the bias in model 1 will be bigger than the bias in model 2, because the bias of model 2 is 0 in the training data. The model 1 will underfit the model, and model 2 will overfit the model. So on the other hand, I think what really matters in machine learning is how generalizable the data is. It doesn't matter how well it fits the training data. The more important thing is how well it can predict the outcome in an independent data set, right? So the connecting dot model will not do very well in the test data, and on the other hand, the linear model will do better. And in this case, the reason is the variance of the model 1 will be smaller than the variance of model 2. So model 2 is actually overfitting. So so what is the bias-variance trade-off, and what is the intuition? So basically, we would, ideally we want to find a model that have low bias and low variance at the same time. However, the high variance method maybe represent their training data well, but at risk of overfitting. And algorithms with high bias may produce simpler models that can may fail to capture important regularities and may underfit the data. So there's always going to be a trade-off between bias and variance. And it's very nicely illustrated in a figure like this. The model complexity represents, essentially you can think of that as the number of parameters in the model. And as the model gets more complex, the training error will start to decrease. But on the other hand, if you decompose the training errors into bias, variance, and irreducible errors, you will find that the irreducible error is something that you cannot improve. But on the other hand, as model complexity goes up, the variance tend to increase, and the bias tend to decrease. And the overall pattern is, it's a bell-shaped curve. At first, as model get more complex, your overall error started to decrease. And then after a while, your model get more complex, you started to overfit the data, your errors started to rise again. So that's usually what we mean by overfitting. So you will have a local minimum that attains a nice balance between bias and variance. And so it's really, depending on the joint force of the two will determine how well the model performs. And so this is a mathematical illustration. So this is the bias, which basically is the expected value minus the truth, which measures the bias squared. And the expected value, the expected value of the differences between the prediction and the expectation of the prediction measures the variance of the model. And they are part of the irreducible error because your features lacking information, based upon the information you have, there are some errors you can never avoid, you can never eliminate. These are called irreducible errors. So mathematically, it satisfies a very elegant three-component decomposition of the total errors. So that's all, it's a foundation for the bias variance trade-offs. So that usually works well for traditional, explains well the traditional machine learning models. But if you have a deep learning model with millions of parameters, even billions of parameters, why would that continue to work well? So what are the reasons why the deep learning model can perform so nicely in a lot of the complex tasks? That's a scenario that people describe as double descent. So what is double descent? Double descent is the best model. Double descent is basically capturing something that is shown in this figure. So there is a set of what we call the under-parameterized model, which is more like the traditional machine learning model, where as the model complexity goes up, the overall error started to decrease, and then after a certain point, the variance started to be bigger than the decrease in the bias, and the error started to rise again. On the other hand, as the deep learning model is actually scaling very well for the number of parameters. In fact, you actually observe a second descent. That's why it's called double descent. Part of a lot of the models, as they are over-parameterized, it started to fit better with the data again, and the error started to decrease. So that's an observed pattern for the double descent. So to give you some illustrations for this, so this is a set of like a sinusoid curve. And obviously, the simplest model you can fit is a regression line with a straight line. Obviously, it's not fitting well. And you're actually somewhere at here where you have a very large error, largely due to the bias. And then as you started to add more reflection points into these spline-based model, you started to decrease the error to a certain point, and you can see it fits the model relatively well, and the curve is relatively smooth. And as you continue fitting the model, it started to vary a lot, right? I mean, it tries to fit every data point, and it started to overfitting. So as you decrease the bias, the variance started to increase, and overall, together, the bias and variance, the joint force together increases the overall error. But on the other hand, if you continue to increase the complexity of the model, it actually started to smooth out different curves, and actually the model started to fit the data better again. And the errors you obtained in this place is the error you observe in this place will be comparable or even better than the errors that you observe in the first descent. So that is one of the potential explanations of why deep learning models are so powerful in many applications. Although I want to emphasize that you still have to be cautious about choosing the right machine learning model. Deep learning model is no doubt very powerful, but it's not a recipe for panacea for every problem. And there are indeed problems where simpler models still is a method of choice and still works better. I'm not saying that deep learning model wouldn't catch up in those areas later, but at least for now, many of the simple models tend to work well in many applications. So when you encounter a problem in your research, in your clinical care, make sure that you choose the best model. Do not be overly obsessed by deep learning models. Sometimes simpler machine learning models could still outperform deep learning models, at least for now. I think that's all I have, and so I listed my email here, and if you have any questions, let me know, and I'm happy to chat or answer any questions. Thank you. Yeah, so the question is, what happens in the second descent? Why is the model complexity increase over there? Over the second descent, tend to decrease the error overall. Yeah, I think that's a very good question. I think it's maybe best explained by the example that are shown here. So I think in the first descent, originally you have an underfit model, right? You have a linear regression. And then it started to adding some complexity, adding those knots. It started to getting a little bit smooth. So it basically fit the data better, at the same time do not vary wildly. So it actually helps decrease the error. And then the problem is that if you continue to add those knots in the spline-based model, you basically increase so much variability, and the model started to become not so smooth. And so you observe patterns like this where the variance the increase of the variance outpace the decrease in the bias. So the overall error increase. But as the model gets even more complex, I think the model tends to capture some subtle patterns of the curve better. And actually, if you observe the fitted curve, it started to get smooth again. I think getting more smooth and getting rid of these high jumps in these places helps reduces the variability. And at the same time, the more complex model decreases the bias. So I think that's why some of these methods could potentially have a second descent that eliminates the error. I think, in my personal experience, I think deep learning model is highly parametric in a way that it becomes non-parametric, because it can actually capture very complex patterns which traditional parameterized model can no longer handle. I think because of this non-parametric nature, it can capture very nonlinear patterns very well. I think that's actually shared by a lot of other methodologies in traditional statistics as well. Like non-parametric Bayesian is actually you have a highly parameterized model. You started to actually capture some subtle nonlinear patterns a lot more nicely than a simple model. Yeah, that's a very good question. I think it really depends on whether somebody already looked at the problem before. Like, for example, a lot of the deep learning work is to refine existing models. And there are a lot of interesting ideas. For example, if you look at the imaging literature, the CNN convoluted neural network models, for example, the future involvement, to further improve the accuracy is based upon going deeper, going more deeper and using a smaller filter and going deeper. I think, you can refine your model along those lines. And if it is a completely new problem, I think depending on, the complexity of the model, I think usually you would want to start from simpler model first and see how well it performs, whether it gives you a satisfactory answer. And then later on, depending on the scale of the model, the number of features, the sample size you have available, I think you can try to get slightly more complex. I think whether you observe the double descent, observing the double descent is not a guarantee. It's sometimes, if you keep increasing the complexity of the model, it's simply, the model performance may get worse. But in some scenarios, it may tend to get better. I think getting to know the literature and knowing what people have tried, I think would give you some clue of where to start with. And then I think sometimes the experience matter a little bit as well. Something that works nicely in the imaging literature may work well in microbiome as well. So some of the ideas may be transferable to other domains. I think that's some of the approach that we use when we use contrastive learning which was developed in imaging, and we use them to make predictions out of microbiome. I think some of these ideas could be transferred, I think, yeah.